The phrase black hole is one of the most powerful and misleading names in all of science. The moment we hear it, our imagination fills with images of darkness, emptiness, and bottomless pits tearing through the universe. We picture a hole ripped into space itself, a cosmic drain swallowing stars, planets, and even light. This image is dramatic, terrifying, and unforgettable. And yet, it is almost completely wrong. A black hole is not a hole in the ordinary sense. It is not an empty space, not a tunnel, and not a tear in the fabric of the universe. In fact, it is the opposite of emptiness. A black hole is a region where matter has been compressed to such an extreme degree that gravity becomes overwhelmingly powerful. It is not a place where something is missing. It is a place where too much exists in too small a space. To understand why black holes are not really holes, we must first understand how the idea of a hole entered the story at all. The name itself came long after the physics was already known. In the early days of gravitational theory, scientists did not imagine holes in space. They imagined massive objects whose gravity was so strong that nothing could escape them. Even light, the fastest thing in the universe, will be trapped forever. This idea dates back more than 200 years. In the 18th century, long before Einstein, scientists like Jean Michel and Pierre-Simon Laplace wondered whether a star could be so massive and compact that its escape velocity would exceed the speed of light. At the time, light was thought to behave like particles, so the idea seemed reasonable. Such an object would be invisible, not because it was empty, but because light could never leave it. Still, even then, no one imagined a hole. They imagined a star, a very dense, very massive star. The concept of emptiness never entered the equation. The modern confusion began in the 20th century with Einstein's theory of general relativity. This theory changed our understanding of gravity completely. Gravity was no longer a force pulling objects together across space. Instead, it became the curvature of space-time itself. Massive objects bend space-time, and other objects simply follow the curved paths created by that bending. In this new picture, a black hole is not a hole punched into space-time. It is a region where space-time is curved so extremely that all possible paths point inward. Once you cross a certain boundary, there are no paths that lead back out. That boundary is called the event horizon. The event horizon is the true key to understanding black holes. It is not a physical surface. You cannot touch it or see it locally. If you were falling toward a black hole, you would not feel anything special as you crossed it, at least if the black hole were large enough. No alarm would sound. No wall would block your path. And yet, crossing the event horizon marks a point of no return. From the outside universe, the event horizon defines what we can and cannot observe. Anything that happens inside, it is forever hidden. Light emitted from within cannot reach us. Signals cannot escape. Information appears to vanish. This is why black holes look black. But darkness does not mean emptiness. Consider a simple analogy. Imagine a deep ocean with a powerful whirlpool. From above, objects seem to disappear into a dark center. But the center is not empty. It is a region where water moves so violently that escape becomes impossible. The darkness is not a hole. It is a boundary beyond which return cannot happen. In the case of a black hole, gravity plays the role of the whirlpool. Space and time themselves are dragged inward. The idea of a hole becomes even more misleading when we consider how black holes interact with their surroundings. A hole suggests something that consumes everything nearby indiscriminately. But black holes do not behave that way. They do not roam the universe devouring stars at random. They follow the same gravitational rules as any other object. If you replace a star with a black hole of the same mass, the gravitational effect on nearby objects remains almost identical. Planets would continue to orbit in the same paths. The only difference would be the absence of light and heat. This fact alone destroys the image of the black hole as a cosmic vacuum cleaner. A hole should pull everything into it. A black hole does not. It only pulls strongly when you're extremely close. So why does the name persist? The answer lies in human psychology. We are visual thinkers. We understand the universe through metaphors. The idea of a whole is easy to grasp. The idea of curved space-time and causal boundaries is not. The name black hole captures the mystery and fear we feel toward these objects, even if it misrepresents their true nature. Over time, the metaphor became reality in the public imagination. Movies, books, and documentaries reinforced the image of black holes as tunnels, gateways, and voids. Science fiction transformed them into portals to other universes or shortcuts through space. While these ideas are fascinating, they are not supported by evidence. In reality, a black hole is best understood as an object, not an absence. It has mass, spin, and electric charge. It can merge with other black holes. It can emit energy through processes near its boundary. It can even slowly lose mass over time through a process known as Hawking radiation. None of these behaviors make sense for a whole. They only make sense for an object. The misunderstanding also comes from language. In everyday life, holes are places where material has been removed. A hole in the ground is empty compared to the soil around it. A hole in a wall is the absence of bricks. But a black hole is defined by the presence of mass, not its absence. It is created when too much matter collapses inward, not when matter disappears. At the center of a black hole lies the singularity, often imagined as a point of infinite density. This is not a hole either. It is not empty space. It is a region where our current theories break down. Physics does not say the singularity is nothing. It says we do not yet understand what it is. This distinction matters deeply. When we call black holes holes, we risk misunderstanding their role in the universe. They are not cosmic destroyers tearing reality apart. They are natural outcomes of gravity, governed by the same laws that shape stars, planets, and galaxies. They are extreme, yes. They are mysterious, absolutely. But they are not holes. To understand black holes, we must first understand stars, because almost every black hole begins its life as a star. Not an ordinary star like our sun, but one born with enormous mass, burning its fuel at a furious pace. These stars live fast and die violently, and their deaths are among the most dramatic events in the universe. A star is not just a glowing ball of gas. It is a delicate balance between two opposing forces. On one side is gravity, relentlessly pulling all matter inward, try to collapse the star into itself. On the other side is pressure created by nuclear fusion in the star's core. This fusion releases immense energy, pushing outward and holding gravity at bay. As long as these two forces remain balanced, the star lives. For millions or even billions of years, this balance holds. Hydrogen atoms fuse into helium, releasing energy that keeps the star shining. The light we see from distant stars is not just illumination. It is evidence of an ongoing battle between gravity and energy. But no star burns forever. Eventually, the fuel runs low. When hydrogen begins to run out in the core, the star changes. Fusion slows, pressure weakens, and gravity gains the upper hand. The core begins to shrink, heating up as it contracts. New fusion reactions ignite, fusing helium into heavier elements like carbon and oxygen. For massive stars, this process continues through multiple stages, creating layers like an onion, each burning a different element. Yet there's a limit to how far this process can go. Fusion only produces energy up to iron. Iron is a dead end. Fusing iron does not release energy. It consumes it. When a massive star's core fills with iron, the source of outward pressure disappears. At that moment, gravity finally wins. The collapse is sudden and catastrophic. In a fraction of a second, the core implodes, crushing matter to densities far beyond anything we can reproduce on Earth. Atoms are torn apart. Electrons are forced into protons, forming neutrons. The core becomes an incredibly dense object, and the outer layers of the star rebound violently, exploding outward in a supernova. A supernova is not just an explosion. It is the moment when the universe reshapes matter itself. The shockwaves forge heavy elements like gold, uranium, and platinum, scattering them across space. Every atom of iron in your blood and calcium in your bones was created in such stellar deaths. What remains at the center depends on the mass of the original star. If the core is not too massive, it becomes a neutron star. This is an object so dense that a single teaspoon of its material would weigh billions of tons. Neutron stars are already extreme, spinning rapidly and emitting intense radiation. But even they have a limit. If the core's mass exceeds that limit, even neutron pressure cannot stop gravity. Then the collapse continues. There is no known force strong enough to halt it. The core shrinks beyond all familiar forms of matter, compressing into a region of space-time where density grows without bound. An event horizon forms around it, sealing off the interior from the rest of the universe. A black hole is born. This process reveals something profound. Black holes are not created by emptiness or destruction alone. They're created by excess. Too much mass, too much gravity, too much collapse. They are monuments to gravity's ultimate victory over all other forces. It is important to pause here and confront a common misconception. The supernova explosion does not create the black hole. The explosion throws material outward, but the black hole forms from what is left behind. The heart of the star collapses inward, disappearing from view not because it vanishes, but because it becomes hidden behind the event horizon. From the outside, it may look like something has been removed from the universe. But in reality, the mass is still there. It is simply trapped in a new configuration, one governed by extreme curvature of space-time. Not all black holes form this way. Some are born through quieter processes. When a neutron star steals matter from a companion star, it can grow heavier over time. If it crosses the critical mass limit, it collapses into a black hole without a supernova. The transformation can be silent, almost invisible, except for the sudden change in gravity. Others are born through mergers. When two neutron stars collide, or when a neutron star merges with a black hole, the resulting object can collapse into a larger black hole. These events send ripples through space-time itself, known as gravitational waves. These waves travel across the universe, carrying information about the violent births of black holes. But the most mysterious black holes of all are the supermassive ones. At the centers of nearly every galaxy, including our own Milky Way, lies a black hole millions or billions of times more massive than the Sun. These giants did not form from a single collapsing star. Their origins remain one of the great puzzles of modern astronomy. Some scientists believe they grew from smaller black holes, feeding on gas and stars over billions of years. Others suggest they formed directly from massive clouds of gas collapsing in the early universe, skipping the star stage entirely. Whatever their origin, these black holes shape the fate of galaxies themselves. This brings us to an astonishing realization. Black holes are not rare anomalies. They are common, natural products of cosmic evolution. They are not mistakes in the universe's design. They are consequences of its laws. When we understand how black holes are born, the idea of them being holes becomes even more misleading. Holes suggest absence, emptiness, or removal. But black holes are created by accumulation and collapse. They are the densest possible expressions of matter and gravity. Even more surprising is how orderly this process is. The formation of a black hole follows precise rules. Its final state is remarkably simple. Once formed, a black hole can be described by just three properties: mass, spin, and electric charge. Everything else about the matter that formed it seems to vanish from the outside universe. This simplicity led physicists to describe black holes with a striking phrase: black holes have no hair. This does not mean they are featureless in reality, but that all the complexity of the collapsing star is hidden behind the event horizon. Yet hidden does not mean destroyed. The mass still curves space-time. The spin still drags space around with it. The charge still affects surrounding particles. The black hole remains an object influencing the universe through gravity and energy. In this sense, a black hole is not a graveyard where matter disappears. It is a vault where matter is locked away from view. The birth of a black hole also teaches us something deeper about the universe. It shows that gravity is not just a weak force acting between objects. Under the right conditions, gravity becomes dominant, overwhelming all others. It reshapes space and time themselves. This is why black holes are so important to physics. They're not just astrophysical objects. They're laboratories where the laws of nature are pushed to their limits. They reveal where our understanding breaks down and where new physics must emerge. To truly understand why black holes are not holes, we must leave behind our everyday intuition about gravity. In daily life, gravity feels simple. Objects fall downward. Heavier things pull harder. Planets orbit stars because of an invisible force reaching across space. This picture works well for most situations, but near a black hole, it completely fails. Gravity, there's not just a pull. It is a transformation of reality itself. Before the 20th century, gravity was understood through Newton's laws. Gravity was a force acting at a distance, instantaneously pulling objects toward one another. This idea worked beautifully for predicting planetary motion and the fall of apples. But it could not explain everything. It cannot explain why light bends near massive objects or how gravity interacts with time. Einstein changed this forever. In general relativity, gravity is not a force in the usual sense. It is the curvature of space-time. Space and time are woven together into a single fabric, and mass and energy tell that fabric how to bend. Objects do not fall because they are pulled. They fall because they are following the straightest possible paths through a curved space-time. This idea is subtle, but powerful. Imagine placing a heavy ball on a stretched rubber sheet. The sheet bends under the ball's weight. If you roll a smaller ball nearby, it will spiral inward, not because the heavy ball is pulling it, but because the surface itself is curved. The smaller ball simply follows the geometry of the surface. This analogy is imperfect, but it captures the core idea. Near a black hole, space-time is curved so severely that all paths lead inward. This is not because something is missing. It is because something massive is present. In ordinary space, you can choose where to go. You can move left or right, forward or backward. Near a black hole, these choices begin to disappear. As you approach the event horizon, the direction toward the center becomes as unavoidable as the flow of time. This is one of the most important ideas in black hole physics. Inside the event horizon, the center is not just a place in space. It becomes a moment in your future. Just as you cannot stop time from moving forward, you cannot stop yourself from moving toward the center once you cross the horizon. This alone shows why a black hole is not a hole. A hole is a place you can avoid or escape from if you're careful. A black hole is a region where the structure of space-time itself removes the possibility of escape. From the perspective of a distant observer, gravity near a black hole appears increasingly strong as an object approaches the event horizon. Light emitted from the object becomes more redshifted, losing energy as it climbs out of the gravitational well. Time itself appears to slow down. Clocks near the black hole tick more slowly than clocks far away. As the object approaches the event horizon, this effect becomes extreme. To the distant observer, the falling object never quite crosses the horizon. It appears to freeze in time, fading and reddening until it becomes invisible. This illusion has led many people to believe that nothing ever truly falls into a black hole. But this is only a matter of perspective. For the falling object, time flows normally. There is no infinite pause. The event horizon is crossed in a finite amount of time. Nothing special happens at that moment. No sudden force, no dramatic boundary. The laws of physics, at least locally, feel the same. This difference in perspective is not a contradiction. It is a consequence of space-time geometry. Different observers experience time differently, especially in strong gravitational fields. The event horizon itself is not a physical surface. It has no thickness. It does not exert pressure. It is a mathematical boundary in space-time defined by the paths light can take. Light emitted just outside the horizon can escape. Light emitted just inside cannot. This makes the horizon fundamentally different from the edge of a hole. A hole has a boundary you can see and touch. The event horizon is invisible, intangible, and defined by causality, not matter. The phrase point of no return is often used to describe the event horizon, but even that can be misleading. It suggests a sudden change. In reality, the horizon is a smooth feature of space-time. What changes is not the environment, but the set of possible futures. Outside the horizon, you can choose futures that lead outward. Inside, all futures lead inward. Gravity near a black hole also reveals another crucial truth. Black holes do not end space. Space continues inside the event horizon. What ends is our ability to observe or influence what happens there. This distinction matters. If black holes were holes, space would simply stop. But in general relativity, space-time does not tear or vanish. It bends, stretches, and flows. Inside a black hole, space and time exchange roles in a profound way. What was once a spatial direction becomes temporal. The center lies not just somewhere you could go, but something you will reach. This is deeply unsettling to human intuition, but it is mathematically consistent. Another misconception arises from the idea of infinite gravity. People often imagine that gravity becomes infinite at the event horizon. This is not true. The event horizon is not a place of infinite force. For large black holes, the tidal forces at the horizon can be quite small. An astronaut falling in might not feel anything unusual at that moment. The true extremes occur much deeper inside, near the singularity. There, space-time curvature grows without bound, and tidal forces become destructive. Objects are stretched and compressed in a process often called spaghettification. But even this is not a hole-like behavior. It is the result of extreme curvature, not emptiness. Black holes also demonstrate that gravity affects not just matter, but light itself. Light follows the curvature of space-time. Near a black hole, light can orbit, circle multiple times, or fall inward. Some photons skim the horizon, trapped in unstable paths. Others spiral inward, never to escape. This behavior creates the iconic image of a black hole, a dark shadow surrounded by a glowing ring. That ring is not the hole. It is light from surrounding matter, bent and lensed by gravity. The darkness is not a void. It is the absence of escaping light. Once again, the image deceives us. We see darkness and think emptiness. In reality, darkness is a sign of too much gravity, not too little. Gravity near a black hole also drags space-time itself. If the black hole is rotating, it pulls space around with it in a phenomenon known as frame dragging. Nothing near the black hole can remain stationary. Everything is compelled to rotate along with space-time itself. This dragging effect creates regions where escape becomes even more complex. There are zones where you can still escape the black hole, but you cannot remain at rest. Space itself is moving. These features have no analogy in the idea of a hole. A hole does not twist time, slow clocks, bend light, or drag space. A black hole does all of these things because it is not a hole. It is an object defined by space-time geometry. When we describe black holes as holes, we impose everyday concepts on a reality that operates by entirely different rules. The truth is stranger and more beautiful. Black holes are places where the universe reveals the true nature of gravity, time, and space. If black holes had a true edge, a solid surface where reality stopped, understanding them would be much simpler. We could point to that surface and say, this is where the hole begins. But black holes do not offer such clarity. Instead, they present us with something far more subtle and far more profound, the event horizon. This boundary is not made of matter. It is not something you can touch, see, or collide with. And yet, it is one of the most important boundaries in the universe. The event horizon exists because of the behavior of light. In physics, light defines what is possible. If light can escape from a region, information can escape from that region. If light cannot escape, then nothing else can either. The event horizon is the surface where the escape velocity equals the speed of light. Beyond this surface, all possible paths light can take lead inward. This makes the event horizon a boundary of causality. It separates events that can influence the outside universe from events that cannot. What happens inside the horizon is not destroyed. It is simply disconnected from us forever. This is why black holes appear black. They are not absorbing light like a black object in space. They are preventing light from reaching us. The darkness is not a surface color. It is the absence of information. From far away, the event horizon seems like a frozen shell. Objects falling toward it appear to slow down, stretch, and fade. Their light becomes redder and dimmer, taking longer and longer to reach the observer. This effect never quite finishes. The object never seems to cross the horizon. But this is an illusion created by gravity's effect on time. For the falling object, the story is very different. Time continues normally. The horizon is crossed in a finite moment. No physical barrier is felt. There is no sudden increase in temperature or pressure, no dramatic warning sign. If the black hole is large enough, even tidal forces can be small at the horizon. This duality of perspectives is essential. The event horizon is real, but it is observer-dependent. It exists as a global feature of space-time, not as a local physical object. This idea challenges how we normally think about boundaries. A wall is the same wall to everyone. An event horizon is not. Its effects depend on where you are and how you observe. The horizon also reveals why black holes are not holes in space. A hole would represent missing geometry, a place where space ends. The event horizon does not mark the end of space. Space continues smoothly inside it. What changes is the direction of time-like paths. The future inside the horizon inevitably leads toward the center. In this sense, the horizon is less like the edge of a pit and more like the edge of a waterfall. Upstream, you can swim in many directions. Once you cross the edge, all currents lead downward. The water does not disappear. It flows. The event horizon also introduces one of the deepest problems in modern physics, the problem of information. According to quantum mechanics, information cannot be destroyed. The exact state of a system should always be recoverable in principle. But black holes seem to erase information. When matter falls in, its detailed structure appears to vanish behind the horizon. Only mass, spin, and charge remain visible. This apparent contradiction has puzzled physicists for decades. It suggests that our understanding of black holes, quantum mechanics, or both is incomplete. One proposed resolution is that information is not lost, but encoded on the event horizon itself. This idea, known as the holographic principle, suggests that all the information about what falls into a black hole is stored on its surface, like a cosmic record. In this view, the horizon is not empty or featureless. It is a dynamic, information-rich boundary. Even if this idea is correct, it does not turn the horizon into a wall. It remains a boundary defined by light and causality, not by matter. Another misconception is that the event horizon is a place of extreme danger. While it is true that nothing can escape once inside, the horizon itself is not necessarily violent. For supermassive black holes, the horizon can be crossed without immediate harm. The true danger lies deeper inside, where tidal forces grow stronger. This again contradicts the idea of a hole. A hole implies an abrupt drop, a sudden transition from safety to destruction. The event horizon is not abrupt in this way. It is smooth and gradual, a consequence of space-time geometry rather than a physical trap. The size of the event horizon depends on the black hole's mass. The more massive the black hole, the larger the horizon. This means that supermassive black holes can have horizons larger than our solar system. Stellar mass black holes have much smaller horizons, only a few kilometers across. This scaling reveals another important truth. Black holes are not points in space. They have size. That size is defined by the horizon, not by the singularity at the center. The horizon is the part of the black hole we can describe and measure. Observations in recent years have allowed us to image the shadow of a black hole's event horizon. These images do not show the horizon itself, but the region where light is captured. The dark center is not a hole punched into space. It is a silhouette created by gravity's control over light. Once again, the language of holes fails us. What we're seeing is not absence, but dominance. Gravity dominates so completely that escape becomes impossible. The event horizon also plays a crucial role in black hole thermodynamics. Black holes have temperature. They have entropy. The area of the horizon is directly related to the amount of entropy the black hole contains. This suggests that the horizon is not just a passive boundary, but an active participant in the physics of black holes. These discoveries have transformed black holes from simple curiosities into central players in our understanding of the universe. They connect gravity, quantum mechanics, thermodynamics, and information theory in ways no other objects do. If black holes were merely holes, none of this would make sense. Holes do not have temperature. They do not have entropy. They do not store information. Black holes do. The event horizon is the reason. It is not the edge of a void. It is the interface between what can be known and what cannot. It is a limit not of space, but of knowledge. One of the strangest truths about black holes is that there is no single, absolute story about what happens near them. Reality depends on where you are. An observer watching from far away and an observer falling into a black hole will describe completely different experiences, and both descriptions are correct. This is not a failure of physics. It is a consequence of how space-time works. To understand this, imagine a distant observer watching an object fall toward a black hole. From far away, the observer measures time using a clock unaffected by strong gravity. As the object approaches the event horizon, something remarkable happens. The object appears to slow down. Its motion becomes more gradual. Its clock ticks more slowly compared to the observer's own. This slowing is not caused by friction or resistance. It is caused by gravitational time dilation. In strong gravitational fields, time passes more slowly. Near a black hole, this effect becomes extreme. As the object gets closer to the horizon, the light it emits must climb out of an ever-deepening gravitational well. In doing so, the light loses energy. Its wavelength stretches, shifting toward the red end of the spectrum. Eventually, the light becomes so redshifted that it fades into invisibility. To the distant observer, the object never quite crosses the horizon. It seems frozen just above it, stretched thin and dim, as if caught on the edge of reality itself. This image has fueled countless misconceptions. It appears as though black holes never truly consume anything. But this is only half the story. Now consider the experience of the falling observer. This observer carries their own clock and experiences time locally. From their perspective, nothing unusual happens as they approach the horizon. Their clock ticks normally. The surrounding space looks distorted, but there is no infinite slowdown. They cross the event horizon in a finite amount of time. No alarm sounds. No invisible wall blocks the way. If the black hole is large enough, even the tidal forces can be gentle at this point. The crossing feels uneventful. This creates a profound paradox. How can one observer see an object frozen at the horizon while another sees it pass through? The answer lies in the relativity of time. Time is not universal. Different observers experience it differently depending on their motion and gravitational environment. The event horizon is a place where these differences become extreme. From the distant observer's perspective, signals from a falling object take longer and longer to arrive. Eventually, they stop arriving altogether. The observer never sees the crossing because information about it never reaches them. From the falling observer's perspective, there is no problem. They continue forward, carrying their information with them. The horizon does not mark a dramatic event locally. This dual reality is not unique to black holes, but black holes push it to its limits. They show us that what we consider real depends on how we observe. This also explains why black holes are not holes. A hole suggests a simple, objective event. Something falls in and disappears. But black holes reveal a layered reality where disappearance depends on perspective. For the distant universe, the object never fully enters. Its information becomes smeared across the horizon, fading into darkness. For the infalling observer, entry is inevitable and unremarkable. Both views are consistent within their own frames of reference. The story becomes even more intriguing when we consider what happens after the horizon is crossed. From a falling observer's point of view, there is still space ahead. There is still time, but the structure of space-time has changed in a fundamental way. Inside the horizon, the direction toward the center becomes unavoidable. It is no longer a choice in space, but a requirement in time. Just as you cannot choose to stop moving into the future, you cannot choose to avoid the center. This does not mean you are pulled by a force. It means the geometry of space-time has redefined what future means. The distant observer, however, can never see this interior journey. The inside of the black hole is permanently hidden. No signal from the falling observer can ever reach back out. This separation creates a kind of cosmic censorship. Nature hides its most extreme behavior behind horizons, protecting the rest of the universe from direct exposure to infinite densities and broken physics. Another misconception arises here. People often imagine that the falling observer sees the entire future of a universe as they cross the horizon. This idea comes from the fact that time slows down near the horizon from the outside perspective. But this does not mean the falling observer experiences infinite external time. In reality, the falling observer sees only a limited portion of the outside universe before crossing. The view may be distorted and blue-shifted in some directions, but is not infinite. Physics does not allow a single observer to witness the end of a universe during the fall. Once inside, the separation becomes absolute. The falling observer's future lies entirely within the black hole. The outside universe's future lies beyond reach. This has deep implications for our understanding of reality. It means that the universe does not have a single shared timeline. Instead, it has many overlapping timelines, each valid within its own frame. Black holes are not holes where reality ends. They are places where reality splits into different perspectives. This perspective-dependent reality also challenges the idea of observation itself.